Hello, grade 12s. So we're going to jump straight into it with this part 2 of genetics revision questions. So the part 1, I hope you've really gone through to make sure that you can hopefully identify where you're potentially making some errors, maybe careless mistakes, not reading the question properly, because these next 3 questions are probably going to be a little bit more challenging for you from a genetics perspective. So make sure that you have a solid understanding of each of them. Okay, so let's go straight into it. First question, what is the probability that the offspring of a haemophiliac man and a carrier female will have haemophilia? So pause the video, do the question for yourself first. Okay, I hope you've done that. So remember, we start with our question A and B. Is it autosomal sex-linked and is it dominant recessive? Now, some of you may be sitting and saying to me, oh, but there's not enough information in this sentence for me to tell. Actually, there is. So remember, haemophilia is one of the disorders, one of the 2 disorders that you need to know from memory is a sex-linked disorder. The other one being red-green colorblindness. So those are the 2 you have to know from memory. It won't be told to you. So first of all, we know therefore that it is a sex-linked disorder. Dominant recessive, where is the clue? The clue comes from carrier female. Again, what does it mean to be a carrier? A carrier is someone who has inherited one of the defective alleles but is not affected by the disorder. Therefore, that cannot be a dominant disorder, because dominant would even be expressed if you were heterozygous. So you cannot have carriers in dominant disorders. Therefore, we know that it is a sex-linked disorder, and it is recessive. Also, we know that it's recessive because from memory, we know that haemophilia is a recessive disorder. Okay, question C, have they assigned letters, or must I use anything? The answer is no, so I have to give my own letters. So, I have said in my example, let those who are normal or the normal gene represent capital E, and haemophilia is represented by little e. Again, it doesn't matter what letters you've used, as long as you can find a difference between the capital and the lowercase, and make sure that it's the same letters. It has to be the same letters. Okay. Parent genotypes, we're told that it's a carrier female and an affected male. So therefore, the female is X big E X little e, because she's a carrier, and the male is X little e Y. Okay. Then we draw our Punnett, and we separate. Again, as a little note here, remember there is no letter on the Y. The Y is blank. Why? Because the things are carried on the X chromosome. They're not carried on the Y, so the Y just stays blank. So we fill in our Punnett. Hopefully this is what you got as you filled in your Punnett. Yeah. For good practice, and just so we know, what is then the genotype ratio going to be? Well, that is going to be 1 X big E X little e is to 1 X little e X little e is to 1 X big E Y is to 1 X little e Y. So there's one of each of them, because they're all different. They've all got different combinations. Okay, so it's the 1 colon 1 colon. What is then the phenotype ratio? Again, don't forget to include the gender, because it's a sex-linked. So, excuse because I just did abbreviations of this, otherwise it wouldn't fit in. But what you would have is 1 normal female is to 1 affected female to 1 normal male to 1 affected male. So you've got 1 of each. There's no saying carrier. We don't define carrier because carrier is not a disorder. You are either normal or you are haemophiliac. And remember, why is this female affected? Because she has inherited both of the defective ones. Why is this male affected? Because he only has 1 to work with, and it's the defective one. But this male is therefore normal because he has the dominant gene. Okay, so hopefully you didn't get tripped up there. Then we get to the actual probability question. The probability question was, what is the percentage chance that their offspring will have haemophilia? And that answer is 50%. Why? Because 2 of the 4 children, 2 of the 4 potentials, will have haemophilia. Therefore, it is a 50% chance. Okay, I'm just going to put a little proviso in with this question, though, just in case some people are getting a little bit eye-twitchy and kind of wondering. Yes, it is true that you generally do not get females existing with haemophilia. If this genetic combination actually happens in the womb, it is more likely than not, like most of the, in fact, all the times, there's no cases of females with haemophilia that this will result in a miscarriage. It will result in this particular genotype not coming to fruition. So that is why haemophilia is basically a males only disorder. So I just use this as an illustrative example for the question, but do know that this does not actually exist in real life. So it's a possible combination that can occur. Obviously you can get carrier females and haemophiliac males, but they will never have actually a daughter who has that. So just a little proviso that I just add to that question. But a good example to practice, again, it could be something else where you don't know that if a female has this, that she will not come to, but we do know with haemophilia that that is the case. Right, we're moving on. Next question. Dalmatian dogs are white with large black or brown spots all over their bodies. The color of the spots is determined by a gene which has two alleles. The allele for black spots is dominant over the allele for brown spots. A breeder crossed two black-spotted dogs and a litter of 9 puppies was produced, which were 7 black-spotted puppies and 2 brown-spotted puppies. Use a Punnet Square to help prove the parents were heterozygous. Okay, a slightly different way to ask the question. Pause the video. Try for yourself now. Okay, so I hope you tried that. Right, question A and B, is it autosomal sex-linked? Is it dominant recessive? So this is an autosomal condition we're dealing with because it's just spots and it doesn't say that it's a sex-linked one. And we know that it's recessive because we're dealing with dominant recessive. You've got the brown, which is therefore only then it's dominant over that. Okay, have I been assigned letters? No, I have to assign letters myself. Okay. So I've said let black spots equal capital D and brown spots equal little d. Now, the way that we're going to answer the question, we're going to start. So the question asks, prove that they are heterozygous. So let's see what happens when we do a heterozygous punnet. So let's let the parents be capital D, little d, so that they are therefore heterozygous. We can draw a punnet, and we fill in. Hopefully you got this as what you filled in. Right, let's do the genotype ratio. The genotype ratio is therefore 1 big D is to 2 big D is to 1 little d. Yeah, so those are your genotype. What is the phenotype ratio? It is therefore 3 black spotted puppies to 1 brown spotted puppy. Remember? Heterozygous means that it will be black spot. There's no carrier, there's no nothing, there's no genders because there's no X's and Y's, it's autosomal. Hopefully you didn't add X's and Y's to this. So, now in answering the question, we need to be a little bit more tactful in answering our question. So we have shown this, therefore, if we did this as a 7 to 2, that would be fine. If we had a brown spotted and a black spotted, that will be different, but we know that we've got 2 blacks. So the only other way that we could have this would be if it was a heterozygous and a homozygous for big D. Or if they were black spotted, they would be homozygous. But what would happen to any of the offspring in that case? They would all have to be black spotted because there would be no way, if there was only one D, so if this D was taken away to be a capital D, there would be nowhere in this punnet that we would get little d. So therefore, they must be heterozygous, as anything homozygous would only produce black spots. If either or both of them was homozygous, the offspring would only have black spots. Okay, so that was a slightly different way of asking, a slightly different way of answering. So please, again, remember, the question didn't ask what percentage chance will they be black spotted, what percentage chance will they be brown. It was a different way of asking. So please make sure you understand what the question was asking. You could have, if this was actually a question, you could have then actually shown another punnet to show that this is what happens if it's homozygous, heterozygous. That would have helped you in terms of your answer from there, just to be a little bit more fuller. Okay, one more question. Barth Syndrome is an X-linked disorder that generally leads to death at a young age. A case exists where a male has survived to reproducing age and has married a normal, non-carrying female. Use a Punnet Square to show the potential genotype and phenotype ratios of their potential offspring. Right, pause, do for yourself. Okay, so I hope you've done that. Right, question, autosomal sex-linked, dominant recessive? Well, we are told in the question that it is X-linked. Therefore, it is a sex-linked disorder. Is it recessive or dominant? Again, I've got these things where normal, non-carrying, whereas a carrying would have been another way. Therefore, it must be recessive. Because it would not matter, again, if I had to specify here that she's non-carrying. That helps you sort of hint at what's happening in the question. So, this is sex-linked, and it is recessive. A little bit of detective work there. Okay, have I been given letters? No, I need to assign them then. So, let normal, the normal gene, equal capital T, and I've said let Barth Syndrome, the disorder, equal little t. Okay. I hope this while at the same time that you're doing the thing where you're writing down all the different possible combinations with this as well, because it really does help you with that. Right, so parent genotypes, we've got a male with Barth syndrome and a non-carrying female. Sex-linked, have to have X's and Y's, so therefore the female is X big T, and the male is X little ty. Hope you got that. Draw a Punnett. Separate out. Fill in the Punnett. So I haven't been asked a probability question. All I've been asked is genotype and phenotype ratios. So, what is the genotype ratio? It is therefore 1 X big T X little t is to 1 X big T Y. Those are the only ones that I can find in this particular one. Therefore, what is the phenotype ratio? I hope you didn't say all normal, because remember, we have to have the genders. So, it is 1 normal female is to 1 normal male. There is no individuals affected with Barth syndrome in this Punnett. Even though these are carriers, we don't talk carrier, we just say that they are normal. You are either normal or you have Barth. And again, lowest common factor, same as what I did here, that is why it is 1 to 1. Okay. So those were slightly more challenging questions. You had to do a bit more investigation to get your answer to that particular question. If you struggled with these, go back, listen, practice for yourself. Understand where I got the differences between dominant or recessive, the differences between autosomal and sex-linked, using the X's and the Y's, doing the genotype and phenotype ratio. Again, like I said, once you understand what you're looking for, once you know how to do these, they actually become quite easy to do. They're actually very straightforward, and these generally count quite a bit of marks. So it's something that you can really practice, have under your belt, and make sure that you have an understanding. There is one more step to add in terms of genetics, in terms of a difficulty that I would say, and that is doing family pedigrees and family trees. And that's going to be the next step that we move on to, which is pretty much the last main meat and bone section of this genetics bit. Otherwise, I hope you guys enjoyed the video. Please go back, make sure you go have an understanding. Otherwise, if you're struggling, hit me up on Skype, get me on Teams, let's have a meeting, let's discuss these things, let's see where you're making mistakes, and let's iron these things out so that we can move forward from here. Thanks very much, guys.